Hey, thanks for tuning in for today's overview. We're diving into something that quietly shapes so much of our tech safety, especially around electrical injuries. Our focus is the world of AV, ICT, and office equipment, like your computers, printers, network switches, basically anything that plugs in and powers our modern lives.
Right. And it's all anchored in a pretty major international standard, the IEC 62368-1 2023 Clause 5. That's the part dedicated to electrically caused injury. The standard itself was developed by international standards committees, and what makes the content we're looking at especially useful is how it links those regulatory requirements to real, everyday devices.
Exactly. The aim is to make sense of safety requirements that, for most people, sound like dense rule books. So instead of just pages of regulations, we'll talk through practical examples from IEC 62368-1, showing why things like insulation, grounding, and special circuit limits matter even in, say, a Wi Fi router. This document isn't just important for big manufacturers, it's like for anyone designing, testing, or even just curious about what keeps our devices from shocking us. Its main claim is that safety isn't just in the test lab, but literally engineered into the guts of every power supply if you do it right.
Definitely. And we'll be pulling apart how different equipment types, like printers or set-top boxes, apply these safeguards. But also why these standards matter for everyone's safety, not just compliance. So let's jump in.
To kick us off, let's talk about why the standard spends so much time on electrically caused injury. Everything in the scope, computers, telecom gear, TVs, is limited to working voltages up to 600 volts, and the core focus is to stop pain or injury from electric shock or burn. What kind of person is likely to touch it? Is it just an ordinary user, like at home, or a trained technician? The standard sorts people as ordinary, instructed, or skilled, and the protection you need kind of depends on that.
Oh, that's smart. So the device knows in a way who's going to be poking around inside it.
Pretty much. And instead of just picking some number for safe voltages or currents, the standard creates categories ES1, ES2, and ES3. ES is energy source. ES1 would be things like a USB output, 5 volts, practically harmless. ES2 is like the analog ring voltage on an old phone line, which can sting but usually not injure. ES3 is stuff like actual AC mains inside a power supply, serious injury risk. Each level gets stricter safeguards. Where it gets tricky is classifying what's accessible and for how long. So, for example, an audio output can be ES2 because short bursts are allowed, but only up to a certain energy and only for a specific time. That's why your phone charger's output is fine to touch, but the inside of its power supply, not so much.
Right. The division's not always just based on voltage. It's about the actual risk, what could cause pain or worse, actual harm. I'm curious, how does this classification actually affect how stuff is built?
It drives physical design. If a circuit is ES3, you have to put in reinforced barriers, maybe double insulation, or design it so only skilled people can get near it, like behind a locked server panel. ES1, you might be okay with just some basic insulation because the energy level is harmless.
That actually explains all those odd insulation layers and service-only stickers on equipment.
Want to walk through what the standard says about insulation materials and strategies?
Absolutely. So one thing that stands out is the level of precision around insulating materials. Like you're not just picking any old plastic for a power adapter. The type of insulation depends on the category. You need basic insulation for the most common cases, but if you're separating dangerous voltages, you might need supplementary or even reinforced insulation. Think of the space between primary and secondary windings in a printer's power supply or the big plastic gaps you see on PSUs and routers. It's not just air gaps either, called clearances, but also creepage, which is the path along a circuit board. Moisture and dust can cause tracking along those surfaces, so you have to consider material groupings and environmental classes. You want the surface distance sometimes greater than the air distance, oddly enough.
So that's why, like a Wi Fi router or set top box might have chunky insulation or even epoxy blobs near the transformer.
It's not just about making it tough, it's about safeguarding the user and meeting those categories for anticipated surges and overloads. They even have requirements for things like testing insulation in humid conditions or doing dielectric tests, pumping 2 to 2.5 kilovolts through the insulation to make sure nothing arcs over, especially after exposing it to heat and moisture. And for antenna ports or internal wiring passing near danger spots, there are like special rules to ensure that even failures don't create a shock pathway.
I always wondered about the gooey fillings in chargers. It's reassurance, not just filler.
Absolutely. And you'll see liquid cooling on high-powered amplifiers sometimes. The liquids themselves also must be properly insulated from high-voltage circuits, which you wouldn't guess at first. Now, once you've built in the right insulation, there's still the component side. How do the safety components factor in, do you think?
Good question. The standard calls out that using a safety approved component isn't a get out of jail free card. Every component, like X or Y capacitors for filtering, transformers for isolation, optocouplers for signal feedback, must meet the right specs, but the entire product still gets tested as a system. One weak link compromises the chain. As an example, a Y capacitor between mains and ground limits noise, but also must have very low leakage current, too much, and you've got a touch safety issue. The same with relays for isolation or MOVs and gas discharge tubes for surge protection. You need the right rating, correct orientation, and you have to test them under real-world faults. That's why component datasheets alone aren't enough for compliance.
Makes sense, right? So after sorting insulation and components, let's not forget grounding and bonding. That's a whole other layer. Proper earthing and bonding is all about connecting accessible metal parts, like a server chassis or APDU in a rack, to protective earth. The green and yellow wire, as most people know, is used for safety earthing, not just functional grounding for filters. The IEC spells this out, and there are national rules for sizes, connections, even tests to prove the resistance is low enough.
And for things like touch current, the part people interact with, those metal trims on a plastic speaker, there's strict measurement for leakage under all operating and abnormal conditions. Even the summation of touch currents from a bunch of ports, like on a 30-port post switch, has to be checked so the total doesn't exceed the limit.
That's something I bet most people never think about. Did you know those tests even account for surge events or, if the ground is broken, using standardized human body network models to analyze fault currents? Plus, if a risky current is found, for example, in a copy or service panel, there have to be interlocks or instructions to prevent ordinary folks from accidentally touching something dangerous. And before we wrap, battery-backed systems like UPS or smart network switches have to prevent backfeeding, basically dangerous voltage appearing at the input after mains power is lost. The standard requires mechanical or electronic isolation, plus labeling and timing protocols, so you don't get surprised by a live plug.
I always wondered about that. Seems like one of those rare but really critical protections as backup power becomes a part of more equipment. So, to tie things together, Clause 5 of IEC 62368-1 weaves together the design, materials, component choices, and test methods into a system for reducing risk of electric injury in our everyday gear.
Yeah, and what sticks with me is how practical the real world examples make this. It isn't just for compliance, it's about safer products in our homes and offices and the fact that every piece, from thick insulation to simple wiring, supports that end.
If you're designing, maintaining, or even just curious about electronics, knowing what each layer of protection does, whether it's a grounded chassis or a relay isolating AUPS, is essential.
For manufacturers and anyone in product safety, mastering these details means fewer surprises and safer outcomes.
Thanks for listening as we unpacked, well, a pretty technical, but honestly crucial piece of what makes modern tech trustworthy.